Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. At the outset of Book 1 of his Optics, Isaac Newton gave a concise introduction to what is now known as geometric optics. As opposed to wave optics, which we will consider shortly, geometric optics treats light very simply as a set of rays whose trajectories are governed by well-defined rules, such as the law of reflection and the law of refraction that we talked about last week. Now, before we go on to explore Newton's theory of light in greater detail, I want to turn to the work of his famous contemporary, Christiaan Huygens. Christiaan Huygens was born in 1629 to a prominent Dutch family in The Hague, which is the administrative center of the Netherlands. He was homeschooled by his father, who was himself a distinguished mathematician and a musician. Christiaan Huygens went on to attend the University of Leiden, where he studied law and mathematics before he attended the College of Orange in Breda. After taking his degree in law and serving briefly as a diplomat, Huygens returned to The Hague in 1654. Thereafter, he devoted much of his time to research and to writing. His work spanned the fields of geometry, probability theory, optics, gravity, astronomy, cosmology, and mechanics. He was also very active in devising and constructing useful scientific devices. For example, in an effort to understand how telescopes work, Huygens and his brother Constantine began to grind their own lenses for telescopes in 1655. This facilitated his subsequent discovery of the Orion Nebula and Saturn's moon, Titan. In 1659, Huygens published a book titled System of Saturn. In it, he advanced the new theory, new at the time, that Saturn's recently observed protuberances or bumps on its side were in fact a solid ring that surrounded the planet. During this time, Huygens also devised a new means for accurate timekeeping, the pendulum clock, which would prove useful in astronomical observations and to a lesser extent in seafaring navigation. In 1673, he published a book titled Horologium Oscillatorium, in which he described the construction and the theory of operation of the pendulum clock. Huygens' interest in astronomy is evident in his book on optics, the Treatise on Light, which was originally written in French in 1678 while Huygens lived in Paris. Several chapters from the 1912 English translation of this work by Sylvanus Thompson are included in the chapters we'll be reading this week. Huygens begins his treatise on light by reminding the reader of some of the well-known properties of light rays. I want you to think about what are these properties, and how does he attempt to explain them? Perhaps most interestingly, do you think that these properties of light demand an explanation? And what does Huygens think? So let's begin looking at his preface. This is on page 158 of A Student's Guide Through the Great Physics Texts, Volume 3. He starts out this preface by explaining some of the previous work that was done by himself. He says in France 12 years ago, and what he's doing now is he's expanding on the work that he had previously done. And he says there are a few other topics that he's adding to this, specifically the study of Iceland crystal. We'll come back and talk about Iceland crystal a bit later. It's calcite crystal. It's very famous because it is birefringent. That is, it bends light in two different directions. He mentions in this preface also that he wrote this in French, hoping that he could later translate it into Latin. He says this at the bottom of page 158. He says, "I wrote it in the language in which it appears in French with the intention of translating it into Latin, so doing in order to obtain greater attention to the thing." Of course, most of the scholars at the time wrote their papers in Latin so that it would be readable by people from all different nationalities, since Latin was kind of the common tongue at the time. He also mentions on the next page, page 159, that his method is going to be less certain than geometry. He says, "There will be seen in this book demonstrations of those kinds which do not produce as great a certitude as those of geometry, and which even differ much therefrom, since whereas the geometer proves their propositions by fixed and incontestable principles, while here, in his book, the principles are verified by the conclusions to be drawn from them. the nature of these things not allowing of this to be done otherwise. So he's mentioning here that whereas in geometry one starts with an axiom and then logically deduces what follows from that axiom, he says in his work it doesn't work quite that way. Rather, what he's going to do is he's going to start with some axioms, find out the conclusions of those axioms, and then look at nature and see if nature is consistent with those conclusions. And if they are, then he says, then these axioms are reasonable or probabilistically correct kinds of axioms to hold on to. Okay, so let's go ahead into his chapter 1. This is on the bottom of page 159, the top of page 160. I'm going to go ahead and read this first paragraph because the first paragraph kind of recalls the state of the study of light at the time. Remember, he's a contemporary of Isaac Newton. He says, as happens in all the sciences in which geometry is applied to matter, the demonstrations concerning optics are founded on truths drawn from experience. Such are that the rays of light are propagated in straight lines, that the angles of reflection and of incidence are equal, and that in refraction the ray is bent according to the law of sines, now so well known, and which is no less certain than the preceding laws. So let's summarize what he's saying here. He's saying what we're doing is we are studying matter, that is nature, and in studying it we're going to be using geometry, but he says the truths are drawn from experience. So he's mentioning here that the things about nature that we know, the truths about nature, we obtain by experimental observations. And here he mentions 3 of them that have to do with light. The first one is that rays of light travel or propagate in a straight line. Okay, so if you have a window covering and it's daytime and you punch a hole in your window covering, a small ray of light will make it through the hole and it will travel in a straight line and fall upon the opposite wall or on, let's say, the floor of your house. The second is that the angle of reflection equals the angle of incidence. We knew this from studying Newton, right? So this was Newton's axiom 2, and Huygens here is just reminding us of this experimental fact. When you have light reflecting off of a surface, the reflection angle is equal to the incidence angle. And maybe I'll just remind you here, if this is a mirror like this, and we have a ray of light that's coming in bouncing off like this, what do we mean by the angle of incidence and the angle of reflection? Well, if you draw a normal or a perpendicular, the theta angle incidence and the angle of reflection are equal to one another. Okay, and the third, he says that in refraction, the ray is bent according to the law of sines. Okay, and so we have called, well, he calls this the law of sines. I would hesitate to call it this because the law of sines nowadays is something different. It's like sine alpha over alpha equals sine beta over, or sine alpha over A equals sine beta over B equals sine gamma over G. So we won't call it the law of sines, so I'll just cross this out. We'll just call this the law of refraction. Or Snell's law, which we saw it in a few different forms. Let's write it this way: n1 sine theta 1 equals n2 sine theta 2. That was the law of refraction. And to remind you what's going on there, if we have a surface between two media, that's medium 1 with a refractive index n1, that's medium 2 with refractive index n2, and if light strikes the interface between these, it is going to bend, and these angles here, so if I call this the angle of refraction, and this here the angle of incidence, maybe I'll call it angle 1 and angle 2. I hope that's clear. Then n1 sine theta 1 equals n2 sine theta 2, and that is the law of refraction. And so what Huygens is doing here is just reminding us of the well-known established truths about how rays of light behave before he goes on. Okay, and now let's continue by looking at the top of page 160. what does he go on to say at the top of page 160? He says, the majority of those who have written touching the various parts of optics or concerning the various parts of optics have contented themselves with presuming these truths. But some, more inquiring, have desired to investigate the origin and the causes, considering these to be in themselves wonderful effects of nature, in which they advance some ingenious things, but not however such that the most intelligent folk do not wish for better and more satisfying or satisfactory explanations. Wherefore, I here desire to propound what I have meditated on the subject so as to contribute as much as I can to the explanation of this department of natural science, which, not without reason, is reputed to be one of the most difficult parts. I recognize myself to be much indebted to those who were the first to begin to dissipate the strange obscurity in which these things were enveloped, and to give us hope that they might be explained by intelligible reasoning. But, on the other hand, I'm astonished also that even here, these have often been willing to offer as assured and demonstrative reasonings which were far from conclusive. For I do not find that anyone has yet given a probable explanation of the first and most notable phenomena of light, namely, why it is not propagated except in straight lines, and how visible rays coming from an infinitude of diverse places cross one another without hindering one another in any way. So that's kind of a long paragraph, but what is Huygens getting at here? He's saying a lot of people have studied the behavior of light. Most people are simply happy with reiterating what these laws are, the laws that we just mentioned a moment ago, those 3 laws. But Huygens is different in that he wants to understand why those laws hold. It's one thing to say the angle of incidence equals the angle of reflection. Why is that the case? And likewise, it's easy to simply say that rays propagate in a straight line, but why do they do that? And he says there are many people who have speculated on this, but most people are happy just repeating those laws. Some have speculated, but he is unhappy with their speculations, and he wants to demonstrate why these laws hold. And there's one thing that he brings up at the end here that is fascinating. He says it's perplexing why it is that you can have light coming from different directions or an infinitude of diverse places, and they can cross one another without hindering one another in any way. So imagine, to kind of bring this, to sharpen this point a little bit, let me give an example of what he's talking about. Suppose we have 2 flashlights, okay? And we aim the flashlights at one another, like this, and you turn them both on so that the light comes out of this one and light comes out of this one. Okay, I'm just kind of drawing these wiggles here to represent the light coming out. And he says it's really strange how these light rays, the one coming from the left and coming from the right, can pass right through one another without hindering each other. Now, this might sound like a strange question to you. Why would, I mean, obviously light travels through other beams. That's not a problem. Well, it is if you have certain conceptions of light. And he's going to talk about one of the popular conceptions of light, and that is Newton's views on light. Newton thought that light itself was a particle. That is, if you were to turn on, I'm going to erase what I just drew because that's... So according to Newton, Newton's view was that when you turn on a light bulb, there are tiny particles of light that fly out of the flashlight, little corpuscles. And this one as well, Newton's theory. So this would be Newton's theory of light, or the corpuscular or particle theory of light, was that these light particles fly out. And if you think about it this way, it is perplexing why those light particles don't bounce off of each other and fly, kind of collide in the middle when they hit, and fly off in different directions. Why don't they interfere with one another? If you have this particle theory of light, it seems that there's a problem, is that how do light beams pass through one another? How do they pass through one another if they are composed of material particles, as Newton hypothesized? That's the problem that he's bringing up here. So he's unsatisfied, we're going to find, with this particle theory of light, and he is going to advocate a different theory of light, which came to be known as the wave theory of light. So we're going to be exploring what he thinks about light. So he goes on to say, I shall therefore essay in this book to give, in accordance with the principle accepted in the philosophy of the present day, some clearer and more probable reasons. Firstly, of these properties of light propagated rectilinearly or in a straight line. Second, of light which is reflected on meeting other bodies, so the law of reflection. And then I shall explain the phenomena of those rays which are said to suffer refraction on passing through transparent bodies of different sorts. And in this part I shall also explain the effects of the refraction of the air by the different densities of the atmosphere. So that third point is he's going to explain why the law of refraction holds. That is why light passing through a transparent body, that is entering a transparent body from a different substance, why it bends. And in that context, he's going to talk about the bending of light by the atmosphere, specifically the Earth's atmosphere. And then he says in the next paragraph, I won't read this, but he says he's going to talk about a certain kind of crystal, the Iceland spar or Iceland crystal, which had been recently studied also by Newton, and it exhibits very peculiar behavior. And so he mentions here that he is going to take a look at those and also talk about how light behaves when it travels through lenses. He has a practical interest in studying the behavior of lenses and telescopes, and he's going to make connection with some of the ideas of Descartes. So that's the same Descartes that came up with the Cartesian coordinate system, and that has the philosophy, I think, therefore I am. You might have come across that in a philosophy course. Okay, and so in the next paragraph, this is the last full paragraph on page 160, he gives his view of what light is. He says, it is inconceivable. So this is where he gets into his ideas. It is inconceivable to doubt that light consists in the motion of some sort of matter. For whether one considers its production, one sees that here upon the earth it is chiefly engendered by fire and flame, which contain without doubt bodies that are in rapid motion, since they dissolve and melt many other bodies, even the most solid. Or whether one considers its effects, one sees that when light is collected, as by concave mirrors, it has the property of burning, as a fire does. That is to say, it disunites the particles of bodies. This is assuredly the mark of motion, at least in the true philosophy, in which one conceives the causes of all natural effects in terms of mechanical motions. This, in my opinion, we must necessarily do, or else renounce all hopes of ever comprehending anything in physics. So what is he saying here? He's saying that he is going to understand light in terms of the motion of matter. I'll write this down. Huygens' theory of light. Huygens' theory of light is that light consists of motion of matter. Okay, motion of matter. But he's not going to say that it's particles of matter flying from one place to another. He has a bit more sophisticated notion of what he means by the motion of matter. And he gives as reasons, so why does he think this? Well, he says that because when you have fire or flame, he understands fire or flame in terms of mechanical theory of atomic motion. So flame or fire, heat consists of bodies that are in rapid motion, kind of vibrating atoms or molecules, and that causes objects to melt, even the most solid objects. And he mentions that if you collect light using a lens or a mirror, then it can cause fire to begin. And he says this is a mark of it being a material substance. Okay, so it's a mark of motion. And he mentions that this is what true philosophy is that it conceives the causes of all natural effects in terms of mechanical motion. So he says the true philosophy, according to Huygens, true philosophy equals that the causes of all natural effects should be thought of. In terms of mechanical motions. Okay, now this might sound correct to your ears, but I want to point out just how radical this idea is. This is a major shift from the thinking of earlier philosophers, and I particularly want to draw your attention to some earlier thinkers such as William Gilbert and the older medieval thinkers who did not try to understand all natural effects in terms of mechanical motions or material causes. What Huygens here is doing is saying we have to think of all things as arising from material causes, matter in motion. Remember, the Aristotelians and later the medievals after them thought in terms of four causes: material cause, formal cause, efficient cause, and final cause. And until you understood all four of those causes, you didn't really understand things in nature. But so Huygens is really making a break from the medieval way of thinking, the medieval and scholastic way of thinking. And Huygens, like Descartes and other of the moderns, really rejected the notion of forms, specifically substantial forms, as being necessary to understand natural effects. Okay. So he says on the last paragraph he says, according to this philosophy, this is on the bottom of page 160, he says, according to this philosophy, one holds as certain that the sensation of sight is excited only by the impression of some movement of a kind of matter, which acts on the nerves at the back of our eyes. There is here yet one reason more, he says, for believing that light consists in a movement of the matter which exists between us and the luminous body. So while this might sound immediately plausible to your ears, perhaps you never even considered that there could be any other explanation of this, it really is, I emphasize, a radical position, which would later cause much confusion, in fact, when thinking about things like electric and magnetic fields. So let me say something about that. So we are right now in like the 1690s with Huygens, and he's advocating this purely mechanical view of science, and specifically all philosophy. He wants a mechanistic view where everything can be accounted for in terms of the motion of material things. Later on, we're going to get to the work of Michael Faraday in the 1850s, and he is going to be studying magnetic fields and electric fields. And I think it's apparent, he's bought into this mechanical idea that everything must have a material explanation. Why is that? Because he's going to argue that magnetic fields have a physical material existence. He was basically implicitly accepting that all natural effects are caused, as Huygens here claims, by the movement of some kind of matter. So if a magnet aligns a compass needle, then there must be some material substance in the space that is separating the magnet from the compass needle. And that he calls a magnetic field. It's some sort of subtle fluid or material that really communicates the force from the magnet over to the needle. But here's the problem. This magnetic field is invisible. You can't see it, and it's weightless. So what kind of a material cause is this? And here I'd only like to point out that perhaps some of the older thinkers were right. Recall how someone like William Gilbert refers to magnetism not as a material cause, but rather as a formal cause. Okay, so I'm going to stop there and just kind of leave you with these philosophical ruminations. And next time I'll continue on page 161 and talk about some of the reasons why Huygens believes his theory of light that he's about to describe.